Hello and welcome to ATI 4205. Order picking is the most labor-intensive operation in a warehouse. Regardless of the product handled or the picking method and equipment used, locating product by the frequency of picks should be incorporated into the system design. The fastest moving product should be stocked as close as possible to the point where it's gonna be picked and at levels that are easiest to pick from for the picker to pick from. Even if you are using an automated storage and retrieval system unit, the retrieval time will be less or should be less the closer the location that is to pick and the point that should be used for picking these items. As we said, order picking is the most important process because it's most labor intensive process. So order picking can determine the level of service experienced by the downstream customer. Anything that we do in order picking, any delays will affect the customer order, will affect customer directly. Travel time to retrieve an order is direct expense and that time affects customers. The faster an order can be retrieved from the shelf, the sooner it's available for shipping to the customer. Order picking consists of three main activities. In the first activity, the person or the machine will travel to the location of the stored item, which is the most work and non-value added activity but required to support the retrieval process of that item. The second activity is searching for the item locally within a bay or a shelf to find the exact location and item wanted. Again, this is a non-value added activity, but essential to avoid picking the wrong SKU number. The last activity is the reach, grab, and put in a box or put in a bin, so it will be shipped, which is a value added activity. This is the only one that's value added activity, and it is the warehouse activity most resistance to automation. It's very hard to automate this kind of process, especially if we have smaller items and different items. In low volume distribution, such as service parts, customer orders will be small, urgent, and different from each other. Consequently, order pickers may travel long distances for each pick, and their path through the warehouse may be quite different even from order to order. The challenge is to reduce travel time by finding an efficient route to get to the required locations and pick customer items. In high volume distribution, such as the supply of retail stores, for example, customer orders will typically be large and may be similar, the same boxes or the same pallets that's been ordered. Each order picker is likely to make many picks per unit of distance traveled, and all order pickers are likely to follow a common path. The challenge is in such order picking is to keep the work flowing smoothly by eliminating any challenges, bottlenecks, or problems. McMaster-Carr is an example of low-volume distributor of hardware and tools. This company distributes over 450,000 different products from four North American distribution centers. Fast service is very important for a customer with large capital equipment or construction project waiting for those parts or those tools. Therefore, McMaster-Carr begins picking the order almost immediately on receipt, even though it might be for only 2 or 4 products or items. It's a problem of sequencing the locations to be visited to reduce travel time or total travel time, knowing that each trip into a warehouse may follow a different path. The pick path can cause a problem, can cause a bottleneck, and can increase response time, which will affect the company's customers. The path need to be optimized. The problem of visiting giving a set of locations as quickly as possible has been nicknamed the salesman problem, which is a very well-known problem. You can search it. Although it has been studied a lot, there is no known fast solution technique that works for all cases and all items. Randomly generated instances, even small ones, can be surprisingly time consuming to solve. Optimum or even good solution can be complex and hard to describe. Order retrieval in a warehouse presents a special case of the traveling salesman problem, in which travel is constrained by aisles. Although the special structure of the problem makes it possible to find optimal solution by computers, most warehouse management systems don't support pick path optimization. For example, the warehouse management system does not maintain any level of information of the warehouse layout design and measures for an algorithm to find the optimum path. So if I don't have the information, I will not be able to find the path. Or it differs from one place or one warehouse to another and time consuming to maintain. So if I'm using the same management system in two or three warehouses, but the warehouse is different, the layout is different, the design is different, then it cannot be used. Or if the optimized path was not communicated to the picker, which will be at that point useless. You know the optimized path, you did create it by the system, but it was not given to the picker to implement it. That's a big problem too. Although the optimized path was defined in most cases, in the warehouse management system, or the warehouse management system will tell the picker the sequence of locations, not the actual path to follow. So already we found it in the we found the optimized path, but we give the picker the sequence of locations instead of giving them the path. So the picker must figure out the shortest path from location to location, and this can be hard to do because order pickers work under pressure and with only local information. In addition, if the picker is using a radio frequency scanner to pick the items, he or she will see only one item at a time, while if using it's digitally displayed on a screen, so they will not see more than one item. While if using a paper pick list, the picker can see all the list, all the items, and plan for the shortest path to get from one location to another. A universal or global path of picking items is hard to find. If the efficient path was computed, then it can be used many times. The problem of finding a good global path through the storage locations is known as the probabilistic traveling salesman problem. And we need to add the probability of doing that or implementing that or finding that to the solution. What will be the likelihood to do that? A good global path solution or a good global path should provide short subpaths on the customer orders and help the picker visualize the next location and how to travel there most directly. The path should be short for most orders and yet is simple in structure when you structure it or when you find it, so the order pickers can understand the sequence of activities that need to be done. An effective path will account for the physical layout of racks where the most popular items are stored. Management may develop simple rules by which the path outline can be adapted for a particular customer's order. Instead of embedding the path decision making in the warehouse management software or management system, the management can provide order pickers with a set of rules to adapt the path, leveraging their intelligence in making the proper decision based on the rules. So give them a chance, give your employee a chance or the picker a chance to use their intelligence in making the decision and traveling from one location to another directly. The simplest path outline is that along a single aisle. This configuration is typically found in a fast pick module of a distribution center. A commonly found path outlined through static shelving is the so-called serpentine pick path. The path includes one-way direction of travel in each aisle, which means that it may be possible to conserve floor space by using narrow aisles. You don't need uh, two lanes for people to travel. One lane will be enough for the person or the picker to travel within the aisle, and that will be narrow. Being narrow, you can utilize the space to add more shelving. However, location sequence might not give optimal travel paths. If the order does not contain items from aisle 3 and 6, for example, as you can see in the figure, then that will be a waste of time to go through that aisle without having items in that aisle. Why do I need to go there into those aisles? So we need to give the pickers the option on what to do and how to make that decision. The problem of one way can be solved if the first few aisles contain the most popular products. So the most shipped products or popular products or picked products can be on shelf 1, 2, and 3. And if other items needed, it will rely on the intelligence of the order picker to adapt the most effective path. Since the picker can skip some aisles, the path outline cannot guarantee and cannot be guaranteed in advance in which direction the picker may travel. So starting from aisle 4 of the warehouse, the aisles will be wider and will be two-way or two lanes travel. So we make space between the lanes. You can see here from 1 to 3 we have one lane, and then the spacing between the aisles became bigger. Another common type of pick path is the branch and pick, which sequences only the aisles and not the locations within an aisle. The pick path passes a reduced set of locations mapping where the fastest moving items should be stored, and the picker detours as necessary into the aisles. This picking path is typically used when there are shallow aisles with some slow moving products. That's why you can see those aisles are short and shallow, and you can travel all the way to the end of the aisle and come back, bring the items wherever the items are. This slide shows an example of a travel path generated by detouring into the back, detouring into and back out of aisles. So you can see if I start at this point and go all the way, I can pick the item A and then go to this aisle and pick item B, then go around and pick item C, come back, pick item E and D and come back and then exit. Travel can be reduced by allowing picker to determine entry and exit from each aisle. So instead of coming into C all the way to C and coming back to the end of it, I can just turn from the other side, turn around, get E and D and come back. So I can ignore this part and just go from here, sorry, go from here around, go to C, pick E, D, and come back and then exit. A much shorter travel path is possible if popular items are stored close to path outline. So instead of being all the way inside, can we bring them closer to the path so I don't have to go deep into the aisle to pick these items? You can compare the figure on the left where the picker must travel deep in certain aisles versus the figure on the right where most popular items are closer to end of the aisle or closer to the path outline. To compute optimal pick path requires the computer to know the shortest distance between any two locations in the warehouse and the corresponding route of travel. Reading through the body of knowledge, until now, there was no warehouse management systems or system that can manage an explicit geometric model of the layout of the warehouse. Therefore, true pick path optimization is not currently done. The fundamental result is, or in pick path optimization, is credited to Ratliff and Rosenthal, um, who gave an algorithm for quickly finding the shortest tour of a set of locations in a warehouse. Using their algorithm, you can find the shortest pick path, subject to the constraint that the aisles can be visited out of their natural sequence. Because of the constraint associated with that algorithm, the suggested path may be slightly longer than the unconstrained optimum. But this algorithm is the same spirit as the optimum findings algorithm, but is much simpler and so easier to program and explain. Any unnecessary travel required because of the no backtracking restriction is generally small. The generated path is simpler in structure than an optimum path and so easier for an order picker to understand and follow. In the dynamic programming algorithm proposed by Ratliff and Rosenthal, an optimum path can assume only a limited number of patterns at each end of an aisle. The restriction that the picker can never revisit an aisle reduces the number of possible patterns to only two. With the assumptions that each order picker is following this rule, pick all the required items from the current aisle and travel forward to the next aisle. In this case, an order can either travel all the way through the current aisle, picking as necessary, or else enter the aisle and as far as necessary to pick all required items therein, and then return to the same end of the aisle from which it's entered. The example in this slide shows how to optimize the path with forbidden backtracking, which means the order picker must visit aisles or aisle I before visiting aisle I plus 1. We have a starting point and end point as shown in the figure to the left here. This is the start, this is the end, and we need to see if we can figure out the shortest or optimum path. Now remember that you can stop at any of these end of the aisle points. Comparing the two allowed patterns and calculating the path, we find the following. Going in one direction all the way into the aisle or picking up the item and coming back in the opposite direction to go to the next aisle. Those are the choices that we have. Either we go all the way to the next or to the end of the aisle and then move to the second aisle, or we can go in just to pick up the item and come back and go to the next aisle. The distance between the points at the end of the aisle is 4. The distance between points from the end from one side of the aisle to the other side of the aisle is 12. So to travel from 1R to 1L, it will be 12, and to go to the next aisle is 4. 12 plus 4 is 16 points, or 16 steps, or 16 whatever the distance or units are. 16 units. If I go from 1R to the item, pick the item and come back, going in, we have 1 point and then we have 3 points here, that's 4. So going 4 in, 4 out, that's 8. And then going to the next aisle is 4, that's 12. Moving to the next aisle, we have 4 options now. When I got to this point or to this point, we have 4 options. From this side, I can go all the way to the other side of the aisle and move to the third lane or third aisle. I can go in and come back. If I was to go to the other side, I went from 1R to 1L and then from 1L to 2L. Now from 2L I can go all the way to the end of the aisle for 2R and then move to the third lane, or I can go all the way in until I get all my items, come back to 2L and then move to the next aisle using 4 points or 4 units. We continue with the same analysis in the next aisle and look at the different options until we get to the end point, to the last point, which says end here. The shortest path is the one indicated in red here. For other orders, only the lengths of the edges along each side of the path need to be updated to reflect new customer orders. This approach can be extended naturally to handle the addition of cross aisles, although the work to solve will increase quickly. So the path will be from 1R to 2R, 2R to 3R, from 3L, from 3L to 4L, and from 4L to the end. And as you can see, from 1R to 2R is 12 units, from 2R to 3L is 16 units, from 3L to 4L is 20 units, and from 4L to the end is 12 units. So that will be all for this session. If you have any questions, please let me know. Thank you and have a great day.